Hey, what's up everybody? In this video we're going to talk about formulas and names of ionic compounds. So we're going to learn how to write the formulas for ionic compounds, and we're also going to learn how to name them. So I'd like to start with a brief review of what ionic compounds are. Now remember, with ionic compounds we have metals and nonmetals as opposed to molecular compounds where we have nonmetals only. And the metals lose electrons to form cations, which are the positively charged ions, while the nonmetals gain electrons to form anions, which are the negatively charged ions. And one of the most important things about ionic compounds is that they have a total charge of 0. And this implies that the cations and anions must cancel one another out. So that means that the total charge coming from your cations has to neutralize the total charge coming from your anions. This is going to be very important when we go into writing formulas for these things. And remember, when we write formulas for ionic compounds, what we're writing is the formula unit. And a formula unit is basically the smallest electrically neutral collection of cations and anions. So ionic compounds are interesting because they don't form these individual discrete molecules. Instead, they form a big, huge, what we call a lattice. And a lattice is basically a repeating three-dimensional array of alternating cations and anions, and it continues infinitely outward through the entire solid. So instead of writing exactly how many cations and how many anions there are in the whole thing, what we do is we write this nice short thing called the formula unit, and that helps us keep track of what the ratio of cations to anions is. So with that in mind, let's do a couple of examples of writing formulas for ionic compounds. So let's start by writing a formula for an ionic compound that's composed of aluminum and chlorine. So remember that aluminum and chlorine, these are both elements that actually form cations, or excuse me, they both form ions that have predictable charges. So if we refer to this periodic table here, all of the elements listed here form ions that have predictable charges, and the reason why they do so is because they're trying to have the same number of electrons as the nearest noble gas. Remember, noble gases, these are very stable, and as a result they're very unreactive. So you can think of the other elements nearby as sort of jealous. They're jealous of the noble gases. They want to have the same number of electrons as the noble gases. And so in the context of metals, that means losing an electron or two. And with nonmetals, that means, gaining a couple of electrons or one electron or whatever. So aluminum loses 3 electrons to form the Al3 plus cation to get the same number of electrons as its nearest noble gas, which is neon. And then chlorine, that's 1 spot away from argon, which is its nearest noble gas, so it only has to gain 1 electron to be isoelectronic, so to speak, with argon, meaning it has the same number of electrons. So the ions that are of interest to us are the aluminum ion, again, which is the Al3 plus, and the chloride ion, which is the Cl minus. When we name anions, we usually add the suffix IDE, so it's called the chloride ion. And well, just looking at this, you can probably figure out what the formula unit is. Again, we're trying to find the smallest ratio of cations to anions that has an overall charge of 0. So it looks like if we leave the aluminum alone, so if we have 1 aluminum atom or 1 aluminum ion, and we have 3 chloride ions at -1 apiece, then it's going to balance out. So our formula unit then is going to be AlCl3. So that's the formula unit for this ionic compound. This is how we would name this stuff. So let's go on to another example. And this next example, we're going to find out what the formula is for an ionic compound composed of aluminum and oxygen. So remember, our aluminum ion, that's the Al3 plus, that doesn't change. What about the oxygen? What kind of ion does the oxygen form? Well, the oxygen is actually going to form, well, let's refer back to that periodic table again. Notice that oxygen is 2 spots away from its nearest noble gas, which is neon. So that means that oxygen has to gain 2 electrons to get that same number of electrons as neon. So that means it's going to form the O2 minus ion, which is called the oxide ion. So let's figure that out. Okay. So again, we have our aluminum ion and we have our oxide ion, which is the O2 minus. And this is interesting because if we leave them alone, in other words, if we have one of each ion, then we're going to have a charge of +1 left over, and that's bad. If we leave aluminum alone, but then we double the amount of oxygen we have, we're going to have a charge of -1 left over, and that's not good. So in other words, we need more than one of each of these ions. So again, like I said, the total charge from the cations has to balance with the total charge of the anions. So what we're going to do is we're going to figure out what the least common multiple of these two numbers is. What is the smallest number that both of these numbers can cleanly divide into? Well, the least common multiple of 3 and 2 is 6. So that means that our total charge coming from the cations must be 6 plus, and the total charge coming from the anions must be 6 minus. And what do you have to multiply 3 plus by to get 6 plus? That's 2. So that means there's going to be 2 aluminum atoms, so Al2. And what do we have to multiply -2 by to get -6? That would be 3. So it's going to be Al2O3. Now, a quick way of doing this is to cross the charges and make them subscripts. So again, we would take that 3 and we would cross it over here, and then we would take that 2 minus and we would cross that over here, and that would give us the same thing, Al2O3. But if you choose to do this method, just make sure that you know why you're doing it. Again, it's because the total charges of the cations has to negate the total charges of the anions. Okay, so that's how to do that. So let's talk about naming ionic compounds. So we talked about writing the formulas for them briefly, but let's talk about how to name ionic compounds. And in the context of naming ionic compounds, there's really two main types of ionic compounds, and those are when there's only one possible cation. That means we have a metal that only forms a cation that has one charge. And then we also have ionic compounds in which the metal forms more than one possible cation. So the way that we name them is going to be different depending on which scenario we have. So let's talk about metals that only form one cation. Well, group 1 metals only form one cation, and those cations have a charge of +1. So if you have lithium or potassium or rubidium or sodium or something like that, all of those metals are going to form cations that have a +1 charge. Group 2 metals, they form cations that have +2 charges, so magnesium and calcium and such. Those are all going to form +2 cations. Aluminum actually forms a +3 cation and nothing else. Scandium forms a +3 cation and nothing else. Zinc forms a +2 cation, and silver forms a +1 cation. So if your ionic compound contains any of these metals, you know what the charge of the cation coming from that metal is going to be. If your ionic compound contains a metal other than these metals, then that means that that metal can actually form more than one type of cation, and you need to identify or specify what charge that cation has. So now I'd like to talk about binary ionic compounds. And binary ionic compounds are ionic compounds in which you have only one metal and one nonmetal. And the way that you name these suckers is you start with the name of the metal, and then you follow it up with the base name of the nonmetal plus the suffix IDE. So let's go through a couple of examples where we name some binary ionic compounds. So this binary ionic compound is, the formula is LiI. So again, we start with the name of our metal, and the name of the metal corresponding with the symbol Li, that is lithium. And the uppercase I, that is the symbol for iodine. So we're going to take that base name and we're going to add the suffix IDE to the nonmetal. So that means this stuff is called lithium iodide. So let's move on to another example. This is Ag2S. Again, we start with the name of our metal. Ag is the symbol for silver. And then we're going to take the base name of this element right here, which is sulfur, and we're going to add IDE. So this stuff is called silver sulfide. So let's move on to another example. Here we have Fe2O3. So this one's a little bit tricky because notice in the case of lithium iodide and silver sulfide, both of these metals were were part of the group of metals that I was discussing earlier. They form only one type of cation. Iron is actually a metal that forms more than one type of cation. Iron can form a +3 cation, and it can also form a +2 cation. So we need to figure out which cation the iron is forming in this case. And the way that we do that is we look at our anion, right? So we know that the oxide ion, let me switch to my pen here. We know that the oxide ion is O2-, right? O2-, and there are 3 of them. So if we take that 2- and we multiply it by 3, then that means our total charge coming from our anions is going to be -6. So that means that the total charge coming from our cations has to be +6, remember, because the cations and anions must cancel one another out. So the total charge coming from the iron has to be +6, and we can see that there are 2 of them. So that means that our iron must have a charge of +3. So in other words, this is the Fe3+ ion. And the way that we name these is a little bit different from the way that we would name these two. The way that we would name this is we would have our iron, and we would also have our oxide, remember the name of the metal and the base name of the nonmetal and the suffix IDE. But then in the middle, what we're going to do is we're going to put this Roman numeral in parentheses. And what this Roman numeral tells us is the charge of the cation. So this stuff is called iron 3 oxide. Notice that the Roman numeral does not tell us how many cations there are. There are 2 cations in this formula unit. But instead, the Roman numeral tells us the charge of the cation. So Fe2O3 is iron 3 oxide, not iron 2 oxide, okay? Okay, so let's move on here. See if I can get this to work. Hang on. Okay. All right. So now I'd like to talk about polyatomic ions. And when it comes to basically what polyatomic ions are, is a polyatomic ion consists of 2 or more covalently bonded atoms that has an overall charge. And the way that we name these polyatomic ions is that you name them as the whole ion. You don't name the individual elements within the ion, you actually name the ion as a whole. So if we look at this here, this is an ionic compound with the formula NH4O3. And this NH4 portion, this is called the ammonium ion, which is NH4+. This is actually one of those rare situations where you have a cation that doesn't have any nonmetals in it. This is possible, but it's not very common. So that's the NH4 portion. And then this NO3 portion, this is called the nitrate ion, and its formula is NO3-. Notice that the total charge on the ammonium is a 1+, and the total charge of the nitrate ion is 1-. So we can see here that the cations and anions are canceling out one another in this case. And the way that we would name this is we would simply call it ammonium nitrate. So that's basically polyatomic ions in a nutshell. And there are several polyatomic ions that exist, and some of them are more commonly observed than others. Here's a table of some common polyatomic ions. It would be a good idea to commit at least some of these to memory, if not all of them, or even more of them for that matter. And the way that you can do that is you can write the name of the ion on one side of a flashcard, and then write the formula for that corresponding ion on the other side of the flashcard, and then just study those for 20-30 minutes a night, and at the end of a week you'll probably have these down pat. But some of the more common polyatomic ions include acetate, that's a fairly common one. Carbonate, that's a very common one. Hydroxide, that's an extremely common one. Nitrite, nitrate, those are both fairly common. Phosphate, that's an important one. Ammonium, as we saw earlier, that one's fairly important. Let's see, sulfite, sulfate, those are fairly important ones. Peroxide, but like I said, you'd want to memorize as many of these as you can, and you don't want to wait till the last minute to do it. So when you write formulas for ionic compounds that contain any of these ions, you have to know what the formula for the ion is to be able to even take a crack at writing its formula, for writing the formula of the whole compound. So let's do a couple more examples here. So we're going to name this compound. This is Pb3PO4 in parentheses subscript 2. Well, notice here that we have the element lead, and lead is not one of those elements that I talked about that had only one type of cation, so we're definitely going to have to use a Roman numeral in this problem. But again, in order to figure out the charge of the cation, we have to first take a look at our anion. And our anion in this case is the phosphate ion, which is PO4 3-. How did I know that? It's because I memorized it. Again, you just can't get around it. You have to memorize these things. So our cation, our anion, that's PO4 3-. And we can see here that there are 2 of our anions, so that means that the total charge coming from our anions is -6. So let me just write it up here. It's going to be -6. So that means that the total charge coming from our cations must be +6. And there are 3 of them. There are 3 lead ions that result in a total charge of +6. So that means that our lead ion must have a +2 charge. So this is the Pb2+ ion. And the way that we would name this, now that we know the charge of our cation, is going to be lead 2 phosphate. Remember, because the Roman numeral does not tell us how many cations there are, instead it tells us the charge of the cation that is in our formula unit. So lead 2 phosphate. Okay? So let's go on to a different one. This one says to write the formula for chromium 3 sulfate. So chromium, this is actually a little bit easier than naming because we already know the charge of the cation here. So our cation is going to be Cr3+, the chromium 3 ion. And then the sulfate ion, again, just for memory, the sulfate ion is SO4 2-. So again, like I said, we have to figure out our formula unit. We have to figure out the smallest electrically neutral collection of cations and anions. And I'm just going to crisscross the charges here. So if we stick the 3 here and we stick the 2 here, that's going to give us our formula, which is Cr2SO4 in parentheses 3. Notice how I use the parentheses here. I put the parentheses around the entire sulfate ion because that's what we're doing here. We're considering the ion as if it's an entity of its own. We're not multiplying the individual atoms by 3. We're multiplying the whole ion together by 3. And remember that, crisscrossing them is a nice quick way to get what you want, but please just understand why you're doing that. It's because the total charges of your cations must balance with the total charges of your anions, and in this case, for cations and anions, that would be +6 and -6 respectively. Okay, so now I'd like to talk about some things called hydrated ionic compounds. And hydrated ionic compounds are ionic compounds that actually contain a specific number of water molecules associated with each formula unit, and these are called waters of hydration. And when we name them, we actually add an additional name to the compound. The way that we name them is we name the regular ionic compound like we normally would, like we just learned how, and then we add a prefix and the word hydrate right after that. So I have a couple of examples of hydrated ionic compounds. This is, the way that we would name this is COCl2.6H2O. This is cobalt-2 chloride hexahydrate. So the hex, that's the prefix corresponding with number 6. So that means since we have 6 water molecules, this is a hexahydrate. And the interesting thing about hydrated ionic compounds is that they can behave quite differently from the non-hydrated ionic compounds. So for example, in this photo here, This photo is these photos are actually both of them are cobalt 2 chloride, but the one on the right, the red one, is actually the anhydrous form of cobalt 2 chloride. Anhydrous means that it is not hydrated, and then the one on the left, the blue one, this is the cobalt 2 chloride hexahydrate. So that's pretty interesting stuff. Another example would be calcium sulfate hemihydrate. Hemi is the prefix that corresponds with 1/2, so there's the 1/2 right there. And another example would be this one. This is copper 2 sulfate. Sorry about that. Copper 2 sulfate pentahydrate. So again, these are hydrated ionic compounds. Again, all you have to do to name them is just add that prefix and the word hydrate at the end of the name. And then to write the formula, all you have to do is just have the coefficient that corresponds to that prefix in front of the formula for water, which obviously is H2O. All right, so there you go. There is how to name and how to write formulas for ionic compounds. I hope this video helped you out a little bit. And all right, you guys have a good one.